Hello folks, everybody ready? I bet you've seen a lot of awesome graphics today, haven't you? Yeah, see any of those WebGL demos? Yeah, great. They folks showed you everything they can do and showed you what the code looked like. But my job today is I'm going to take you through a really simple, very unglamorous, very silly little demo, line by line, and let you see what each line does and how simple it all is. In fact, when I did this at Grace Hopper, we went through it in less than 15 minutes. I've added a second iteration, but that's how fast and how easy you can do this. What I'm going to do is I'm going to explain. I'm going to assume that you know absolutely nothing about 3D animation. So please bear with me if it's sounds a little silly or patronizing, but I'm going to assume that you know just about as much as I did when I got started. So I'm going to explain the concepts, and then I'll show you how it works in the code. And first of all, our goal is to make something that looks like this. The simple little object with a color and a little bit of character maybe. And just move along, and in here a second, it'll pop back through on the other side. Oh, come on, little fellow. There he goes. Okay. So when I think of animation, what's intuitive to me is the way classic 2D animation works. Take some kind of a drawing tool, a pen, or whether it's a virtual pen or a real-life pencil, or something that makes draws a primitive on the screen like an X Windows, and from that assemble an image of what you want to animate from the angle that you want to be seen, and then after that, imagine some small movement, maybe a movement of a character's hand or a slight rotation around it. Draw another picture, and keep building those up one after the other and make a sequence of frames that way. Well, 2D virtual and 2D analog are pretty analogous in that respect. And 3D computer graphics and 3D real-world graphics are analogous in the same way. In fact, 3D animation is a lot more like filming. In fact, the closest analog we have in real life is claymation. That's how Gumby's made. A bunch of little Gumbies. Our Clokey makes a diorama. He builds a box, makes a little scene in the box out of felt and clay and whatever else, and puts a little Gumby in there, makes a little move with the 3D Gumby, and takes another picture, and builds up a set of frames that way. So that's what we do when we create an animation with WebGL. In fact, what we're really doing is, we were to imagine that we were scientists and we created a big bang in a beaker. We have our own little world. We get to do whatever we want in there. We get to populate it with objects, move them around, squish them, stretch them, and play God with them. It's one of the reasons why 3D animation is so much fun. You get to play God. You ready? Okay, we're in this strange little world, this little place we created, kind of like there aren't even any, it's like a strange planet, but there aren't even any planets in there. There's nothing in there. We have to learn to get around. We need to ask ourselves, I wake up drunk someplace, I find myself lost. I ask myself 3 questions. Where am I? What else is here? And how do I get around in here? Or how do I get out of here? So to learn to move around in our little diorama we created, we'll ask ourselves those questions. And 3.js has answers for those questions. Where are we? Well, our diorama, our empty box that we're going to build our little world in, or our beaker, if you please, is what 3 calls a scene. Everything happens in the scene. You instantiate it. You put all the objects in it. It's the container for everything. It's the top level of the big tree of stuff we're going to make. And because this is, an alien little world, all off by itself, we need a way to see in there. When we're making 2D animation, the question of which angle are we looking at, what are we looking at, is already given. It's inherent. but it isn't in 3D animation. If you're taking a picture, you got to take it from somewhere. So that's why we need a camera to look into our little world. What else is there? Well, everything in this little world that we create is called a mesh. I'm sure you've seen wireframes before in old, early computer animation. Something made out of triangles and lines. That's what it looks like underneath. That's the underneath representation. That's why we call them a mesh. They look a lot better now. We've gotten better at representing them, but that's still the logical structure. And because this is a newly created little world in there, we need stage lights. We need to shine a light on the stuff because there's no sun, there's nothing in there. And we have to create that. We create a light, in this case a point light. I'll show you how it works here shortly. And how we move around, we use affine transformations from geometry. Translate, rotate, and scale. All of the meshes have methods for these, and you can create any movement that you're going to need in there. And how we move through space, how we move through time, is this thing you've probably heard of called request animation frame. What we're doing is we ask the browser for an animation frame. Now this is kind of like, a few years back, I heard of this woman doing what was called extreme couponing. She went to the store and she bought a roll of toilet paper, and the deal the company had with this toilet paper was it had a coupon on it for another roll of toilet paper. So she bought the first roll of toilet paper, tore the coupon off, got another roll of toilet paper. As she was standing right there, tore the coupon off again, got another roll of toilet paper. So every time she received one, she tore off the coupon to get the next one. And she built up a huge truckload of toilet paper that way. Or we're going to use the same method, except we're going to build up a series of animation frames. It's a little bit nicer, a little less rude. So now that we know what we need conceptually, what do we need to go shopping for? Well, to make this super simple thing that's just, a hack to get us started, we just need three things. Of course, we need the three.js library. That's going to go in, of course, any three.js application that we write. A Teapots.js, that is the logical data that describes what that teapot shape is. And because this is in a web page, we need a web page. And to get started, that's it. To get it all, I've got it all in the GitHub repo. Don't worry about this. In fact, don't even look at it. I've got a typo in it. So I'm just going to move fast, and I'm going to take to the setup step. Now, I guarantee you, there is nobody in this room who knows less about HTML and CSS than I do. So I'm just going to point you to this and let you know what's going on. The takeaway from here is that you need a canvas. You need to know how big it is. You need to load a couple of scripts. Of course, you need to load 3. And you need to load the script we're about to write. For this little hack, I just left it in there. You'll probably do better than that when you do yours. And finally, the last setup, we know we have this little diorama, and we know we have the real world that has our web page in it. We have to glue them together. That's the job of this thing you call a renderer. We create one, tell it the size of the window it's working with, and stick it into the document. And that's all our setup. Now the part you've been waiting for, the codes. Here comes the real 3D stuff. Before, I talked about the scene, which is our empty box we're going to build our diorama in, and the camera that we use to look at it. There it is in the code. The scene, there's nothing to it. It's just an empty box. So just instantiate one. The camera is a little more complex because we have to tell it which region of space that we want it to be in charge of. It's got 4 parameters to its constructor. A 35, that's an angle. That's our angle of view in the up, down, the Y direction. The second, that quotient there of the 2 window dimensions, that's the aspect ratio of the window it's working with. So the camera can put those two together, and it knows, it can calculate the frustum. It knows the pyramid of space that the camera is going to be able to see. Those last 2 represent what we call clipping planes. It tells how near and how far away the camera is going to look at stuff. Anything closer than 0.1 of these are unitless units for GL. They don't correspond to anything in real life. You get used to that soon. It tells it not to look at anything closer than 0.1 or anything further away than 1,000. That's a huge sweep. It's because I'm basically pulling everything out of my ear to show you how easy it is. As you get used to this, as you get more skill, you'll learn to fine-tune these so that they fit right around your action and show it to its maximum. But for right now, we're just going to wing it. The only thing you really need to keep in mind is that first parameter, 0.1, how close the camera can see. Don't ever make that 0. It's tempting. You want to pull in as much as you can, but that is going to end up in the bottom of a fraction, deep in the bowels of three.js. And when that happens, you'll get really fun-looking stuff on the screen. So just leave it at some small value, whatever it happens to be. And then one more thing that we need to do with the camera before it can do its job. You see, when we put stuff into our diorama, we kind of teleport it in there. It all ends up at the same place. It ends up at the origin of the coordinate system in this little world. So if we don't move stuff around, we're going to get the camera trying to shoot stuff from inside the teapot. So what we got to do is we got to pull the camera back so that it can actually see something. So now's as good a time as any to talk about the coordinate system. It's the same one you're familiar with from high school algebra. X grows to the right, Y grows up, and Z grows straight out at you. If you don't know this by the back of your hand by now, believe me, you will in very short order. So now we got our little world. We're ready to start putting stuff in it. Now we get to see what a mesh is all about. Okay, our teapot, I mentioned earlier that that's described it's a JSON file actually. I actually found on the internet an OBJ file. That's a really common format for shape data that's used by GL. But I had to go through an intermediate step before we could load it. There's a converter deep in the bowels of the three.js tree that you can use to you do this beforehand. You do this conversion beforehand so that it doesn't have to be done at runtime. You turn it into the JSON file, and then the JSON file is what actually gets read in. I know it's long, it's kind of convoluted, and it's not very efficient, but for now it's what we've got. So get yourself a handle, and then instantiate a loader, and then use the loader to read in the teapot. And not only does it use the teapot file itself, but there's something else going on there. There's a callback. Reason is, we don't know how big this JSON file is. It's asynchronous. It could take forever. So we just give it a callback and let it do its thing and then kind of wait. So the callback, here's what it looks like. Its parameter is what we call a geometry. That is the JSON file converted for finally in its final state, converted for use within 3. And then there's something else there. There's a thing called the material, and the material and the geometry go together to add the mesh. So what's the point of that? What does this really look like? What are we really doing with all this? Well, the mesh that has those two parts, you know, as I described a while ago, this is just shape data. This is what was in the Teapot.js file. I mean, you can't even see it. That wireframe there is just there for our convenience. It's actually invisible. It's just a point set and some edges, nothing else. We have to tell it what it looks like. We have to tell it whether it's a wireframe like this, or whether it's shiny or flat, what color it is, if it's got a pattern, if you can see through it or not. And that is the job of the material. The material, think of it as saran wrap. It wraps around the outside of this point set so that it becomes visible. So now with those two parts, we can make more sense of the callback. It takes in the teapot that was read in, creates the material. There are a bunch of kinds of material. This Fong material is nice and fairly simple, but complex enough so that it'll actually give us real-world artifacts that we're accustomed to. It'll shine in the right places. It'll cast shadows. Basic, you don't want that for now. It's tempting, but that's just flat. You won't even light won't bounce off of it. It won't look 3D at all. So the next step up is the Fong material, and we're going to give it a color. So it's a single color thing. And then the two go together to make the mesh. And like everything, we use scene.add to teleport it into our little world, and then give it the handle so that we can use it outside the callback. And now's the part when we get to play God. We get to make our light. We're using a point light. There are a bunch of different kinds. There's ambient light, which just kind of glows everywhere. There are spots. This point light is kind of like a sun or a lamp. It's just going to shine down onto the teapot. So that's what these two parameters are. This is x, y, and z coordinates. We leave it in the middle, pull it out and back a little bit so that it shines, and then add it to the scene like everything else. So now we've got a nice looking little teapot, but the whole point of an animation is for it to move. So now is the time when we get to do that. I'll take you through all the pieces first. To get it to move, we use the affine transformation before. The translation, which is we just assign its coordinates values directly. Here, every time we go through, this is all going to go together in a loop. We're going to increment it by just a little bit. So every frame is going to go a little bit more. And eventually, it's going to go all the way out here. It's going to keep flying. It's going to be all the way out over the water if we don't stop it. So what we do is we test to see if it flies off the edge of the screen. This is just an arbitrary value. You'll probably get to see it turn around a couple of times. But when it's gone, take it and zap its position all the way back over to this side again and let it go back. And keep going over and over. Once we've got the little movement, we have to tell the renderer to do its job. We've got our scene set up. It's time to take the picture. The renderer talks to the scene in the camera and the web page. It's a lot of work behind the scenes, but this is all we need to tell it. And now's when we get to claim our toilet paper. Just tell it request animation frame, pass it the... What this method is that's everything that I just showed you, all rolled into a little function. So we got our arbitrary screen width, create our function, and call it the first time, and then it calls itself from then on, and off it goes. And so we get, back to the demo here, so we get this. And there's our first iteration up and running. It's not much, but we did it. We did it in a very short time. We know a whole lot more than we did when we started. So now that we've got a starting point, we can really start to hack a little bit. How about something that looks like that? Now instead of a teapot, we've got a nice yummy apple. I was hungry when I made this. So I made my teapot look like an apple. I gave it an apple skin, and I changed the shape a little bit to make it look like an apple. And there's some clouds in the sky. We're not just flying kind of aimlessly through an empty box. There's a sense of place now. And you know what else I found out I could do? I can make it respond to the mouse now. And we're not just sitting there watching. We can actually participate now. So let's go back over here. And I'll go through all the steps of doing that. Oh no. Y'all wanted to go over this again, didn't you? I know it took me a bunch of times before I remembered it all. Oh, come on. Let's do it a better way. Where were we? There's where we were. What else can we do? Well, to give the teapot an apple skin is we use what we call a texture. Now, I know the word texture implies that there's something tactile, that there's some kind of surface irregularity going on with the teapot. That's not really the case. What texture means is that we're using an image file to decorate the material. We're going to wrap an image file around this thing like gift wrap instead of just a plain color. So this is really pretty similar to what we did before, but there's just a little more to it because image files are a little more complicated than plain colors. So we use it this is just a plain old JPEG file. I looked on the internet. I found one that tiles seamlessly. And we use a loader similar to the JSON loader to pull it in. And then there are these two S&T things. Now think of S&T as X and Y in the world of the saran wrap going around of this gift wrap going around the teapot. We use S&T instead of X, Y, and Z just to keep them separate. And what I'm telling it here is, if it only makes part way around, repeat it. Put it on a second time. When I put this together, I noticed that my apple skin just kind of went halfway around, and then it was just kind of plain red. That last line of pixels on the edge of the paper, at the edge of the image, it just kind of wrapped them all around. So I gave it this, and now it goes all the way around in both directions, and it looks like an apple. Perfect. And we create the material as we did before, a Phong material just like before, except now instead of the color parameter, we give it a map parameter with that texture. Here's its value. And changing the teapot shape, how I made it tall. That's the third affine transformation that I mentioned. Scale. It just tells it scale things in the along the y-axis 1.5 times their normal size. It only applies to the teapot. So this is actually quite powerful. I didn't get into this here because it's a little beyond the scope of this, but you can actually take basic shapes. There are basic shapes that come with three.js. There are spheres, cubes, it's a torus, and so forth. And you can use those, squish them and stretch them and bend them and come up with all kinds of things. You can take cube, scale it in one direction to make it really long, do that 4 times. Scale another one in the other direction, make it flat, and that makes a table. You can do a lot of things just with the primitives that come with three.js. The teapot's just kind of fun. Besides, I came up with that funny title. I had to use the teapot. But for now, I'm just going to make my teapot look like an apple. And here we go. Actually, you notice it moved differently. Instead of starting at the one side and moving off and then coming back over to the left, it's now going back and forth. It's actually snaking along. And this again illustrates all animation really is. It works the same way as it did in 2D animation. You just keep track of the thing's position and move it. So here we're testing to see if it fell off either end, changing the increment, giving it a negative movement increment to make it move back from right to left. And when we get to each end, flipping it by half, and yes, that is in radians. I know, earlier I showed you the camera setup. The sweep was in degrees, and this is in radians. Go figure. If it bit me, it's going to bite you. So when it happens, don't feel bad. And I'm sure you've also noticed that there are no bounds checks on that rotation. If you let this run for days and days and days, eventually you're going to overflow that thing. I hope you don't. I haven't done it yet. If I ever write a real program, I promise I'll do better than that. And I know you will. Okay, now we get to our blue sky. Before, we just kind of we need to tell the renderer, it's not only responsible for setting up the next frame, it's responsible for wiping the screen clean between each one. And before we just let it go with the default, which was the default color that it snagged from the page. But now we're going to tell it we want a nice sky blue, and 1.0 means we want an alpha value of 1.0, we want it to be totally opaque. And the clouds, how do we do them? Well, we saw what that mesh looks like, all those little triangles. How do we make something poofy like a cloud? Well, there are different ways, but in this instance, we're going to cheat. We're going to use something that looks like a cloud from one angle, but it works like a cardboard cutout. It looks kind of convincing until you look at it from the wrong angle or just look at it hard enough. And then we see it's totally fake. So what we're going to do is, we're going to use a mesh, but instead of a whole big round mesh like that teapot, it's just going to be 2 of those simple little triangles, go together like that, make a pane of glass. And we're going to put the texture on it the same way we did the apple skin. And part of the texture there, part of this image, I just cooked this up in the GIMP in about 2 minutes. Part of it, you see, is transparent. Remember, we can't see those meshes unless there's something there to make them visible. So the parts of this that are transparent, those aren't going to count. When we get it up there, the only thing we're going to see is those poofs. And this is the basic process. That simple little 2 triangle pane of glass that we're going to create, it's like sticking a sticker on it. So this is pretty much what you've seen before. We're going to read in the image file the same way. This time when we create the material, there's a second parameter there. We're telling it, yes, there are some transparent parts here. And then again, this is what you've seen before. This is called 2 because I'm going to do it twice. Those are actually 2 poofs. We're going to create a plane geometry, and those two parameters there give you the height and the width. Notice it's not square. I can make any size of rectangle, any dimension of rectangle I want. And that image, once it's plastered on there, it will stretch and compress to fit it perfectly. So I can make 2 of them. I can make one that's kind of more square and one that's kind of more long, and those clouds will stretch and look a little bit different on each one. Other than that, it's just the same way as we made the teapot. And now that we've got the 2 clouds, put them wherever we want. Move them back a bit, back into the screen so they're behind the teapot. Move them to the side so that both of them fit there. And in one of them, I'm going to rotate by a 1/4 turn. Because that way, that same image file looks like a bunch of different clouds. This is a classic animation technique. Take the same simple little primitives, squish them, massage them, turn them around, and use them over and over in different ways, and build up a huge library of scene like that. So I think this is, oh yeah, those nifty mouse controls. Hey. I have no idea. I think it's just my laptop. Anyway, there are 3 different lines. Pardon?
It said that your battery was about to die.
My battery? I should be plugged in. Maybe I'm plugged in the wrong place. Maybe I should try down here. There's not much left anyway. Give it another try. Anyway, all those complicated mouse controls, I'm sure you folks who are web programmers know what's involved with that. Hang on, let me get my right kernel here. Oh, come on. I'm sure you know about all the listeners you have to set on the mouse, and all the watching you have to do, and when the mouse makes a movement, you have to translate it to the parts of your program. That's all been abstracted away. There's only 3 lines you need to add. I've looked down into the examples in three.js, and I found the file that at least that certain set of mouse movements that encapsulates them. Just load that, and oh, hey, look. All right. Yeah, here we go. Yeah, I found this script called Orbican. Hey, don't do it to me again. Oh, it doesn't like me. Sorry? I have no idea what it's even doing. Well, we're so close to the end now. I'll just verbalize the URL. You've seen the demo. Anyway, just read that script in and declare one, and every time it goes through the loop, tell it to update the controls. And that's it. So the GitHub repo, I had a QR code for you, but I'm sorry, I'll have to tell you verbally. github.com/shegeek, SHEGEEK, /teapots can fly.